So thank you for the kind introduction. Welcome also from my side. Maybe just a slight, a little thing I want to add to the initial words. Yeah, our top goal is a non-functional requirement. I am dealing with a lot of functional requirement, but we will see that in a few seconds. Welcome to the talk. The title is Safety in Security. Is it the same? Is it contradictory or just different, dealing with different stuff? At the beginning, after I introduce myself a little bit further, I want to tackle what is safety engineering. As far as I know, most of the members in the audience are dealing with security engineering. So I will present what I'm doing, what is safety engineering. A little bit of history is necessary to understand why safety engineering is the way it is and why it cannot be the way it is to tackle the challenges of the future. And this will ultimately lead to the link between safety and security. A little bit about myself. I'm a functional safety consultant, and I'm also a part-time lecturer at the FH campus in Vienna. And they were having a course for model-based safety and systems engineering. The most important thing, if you want to ask me question afterwards, this is my email address, and I will also share it again on the last slide. Yeah, also a short disclaimer at the beginning. Functional safety engineering, and please consider also the word functional here, is a little bit different in every domain. It's a little bit different in automotive and avionics, for railway engineering and so on. But I want to give an overview over the whole idea of functional safety engineering. The consequence is that something I mentioned is maybe not 100% true for a specific domain. The terms are maybe not every time the same, and maybe something is missing what is kind of very relevant in a certain domain. But for the overview to get an idea, this is not very relevant. But just if there is a functional safety expert in the audience, this is the reason why. Safety engineering. At the beginning, we need to start with something a little bit boring with basic definitions. So what is safety? What is it about? I have here some definitions taken from functional safety standards. So safety is a freedom from unacceptable risk or the absence of unreasonable risk. The first one is a general functional safety standard, and the second one is from an automotive functional safety standard. And the US military standard 882 says that safety is the freedom from conditions that can cause death, injury, occupational illness, damage to or loss of equipment or property, or damage to the environment. Maybe I should add here that in Europe, safety is basically only seen as keeping people safe to avoid risk for people. But in the US, there was always a more broader focus on safety. Yeah, but what we see is in the first two definitions, we have the unacceptable risk. So what is the risk? It's probably very similar to the risk definitions you know from security engineering. Risk is a combination of the probability of occurrence of harm and the severity of that harm. Very similar definition in the military standard, the combination of the severity of the mishap. So they say mishap instead of harm, but basically the rest is the same. So we can define risk as a product of probability and harm. The higher the probability, the higher the risk. The higher the harm, the higher the risk. And safety engineering is the engineering discipline which assures that the engineered systems are safe. Here, a depiction from an unknown source. Yeah, risk can be treated, and risk is always very different. Even though if I have, for example, low probability, but a high probability but a low impact, we would not consider that this pond here is a big risk. But maybe the probability of impact might be high if we look at the third one, but the potential impact is that high that we also want to avoid that risk, even though the impact, the probability is quite low. So risk is combined out of these two terms, but it is always a kind of a consent needed to determine if a risk is too high or not. But I will come to that later. Okay, what is now the goal of safety engineering? The goal again is assuring an acceptable level of safety of engineered systems. And how do we do that? First, we are defining the scope and the system boundaries of the system under consideration. And then we are starting with the hazard and risk analysis. Hazards are a potential source of harm caused by malfunctioning behavior. And in other words, it's a potential accident. So any scenario that can lead to damage, to harm of people and also of equipment or property, depending on the scope, is a hazard, a potential accident. We need to find these hazards and make then a risk analysis. We will talk about that in the details in a minute. Then we need the definition of the safety goals. Based on the hazards we have identified and on the risk we defined for each of these hazards, we then say, okay, these are our safety goals. We want to assure that a car is not accelerating if no acceleration command was given, for example, no unintended acceleration, that the brakes must never fail, and so on. This is the definition of the safety goals. At the same time, this is the overall. These are the overall safety requirements. Based on these non-functional requirements, often we then start our functional safety concept. The functional safety concept is, as the term is quite self-explanatory, we are defining the function and the functional interactions between these functions in a way that we can avoid these hazards. It should be implementation independent. We should not consider solution. So when designing a car, it's clear that we say, okay, we are talking about brakes, we are talking about an engine and so on, but we should not consider specific components like a microcontroller or from a specific brand, but also not in general, not thinking in solutions, not thinking in a in any kind of warning lamps and so on, just defining the intention, the functional intention. We want to warn something. We want to gain information about the speed of the car and so on, but not defining we need a speed sensor. This is because sometimes we can then find better solutions when we're just concentrating on the functional concept, identify the functional interactions, and in the next step, we start the technical safety concept where we are considering, okay, this needs to be done in hardware, this needs to be done in software, this needs to be done in other technologies, and so on. The next steps are quite similar, like in every other development process. We are developing the defined and designed things. We make unit tests, we make verifications, we then integrate all the components, we test them, and we make a validation. The terms validation, test, and verification, this is one of the things that is treated a little bit different in every domain. But in automotive, the validation is only on system level, so I put validation here. What is also considered in safety engineering is the maintenance, the modification, potential repair, retrofit, or decommissioning disposal. So the safety engineering process does not end when we validated the system, but we also at least need to consider how to maintain the system, what happens when we modify the car or the system, do we have all the documentation prepared, and so on. Yeah, now I want to highlight a little bit more the hazard and risk analysis. It's, as I said, the identification of the hazards, so of all the potential accidents that can happen. And we then need to classify the hazards and assign a level of rigor with respect to procedures and measures needed to achieve the needed level of safety. This is now a generic description of what is often called the safety integrity level. There are also some domain-specific adaptation to that concept. There is the automotive SIL, the motorcycle SIL, the performance level in machinery, and so on. But in the end, we say, okay, for medium risk, we just need to take medium actions. For high risk, we need to take high actions. We need to work with redundancy. We need to work with very reliable components. We need to make more tests and so on. So the level of rigor is always higher, the higher the risk is. Based on the risk, based on the classification, we then formulate the safety goals in order to avoid the unreasonable risk. So what are basically the measures we have to reduce the risk? The best solution always is to eliminate the risk, find another solution, find another concept so that we don't have that risk. The next would be to mitigate it by design, not with a function, with additional measures, but to really reduce it by design. To say, okay, we are not a certain element in the system which is spinning and could hurt people is not spinning that fast, and therefore it is less dangerous, for example. The next thing would be the detection with response. So we can detect a dangerous condition, for example, a malfunction, a broken component, and so on. And then we can react to that. These concepts are often realized by so-called safety functions. And this is what most functional safety standards are focusing on. So they list that you should consider eliminate the risk elimination. Mitigation is part of the standards mostly, but the big part where you have a lot of measures, a lot of information how to achieve that, the big part of the standards deals with the so-called safety functions. Additionally, you have always the possibility to have any warning devices. You can have trainings and procedures that people can know how to react in a dangerous situation in order to avoid potential harm. And the last measure would be to give people personal protective equipment if not necessary to avoid it. Okay, I was talking a lot about acceptable or reasonable level of risk, but what is that? What is acceptable? Who defines that? Yeah, basically this is defined in legal norms and laws, internationally and nationally. And those norms and laws demand safe products and safe systems. For example, the European Directive on General Product Safety lists a few things that can help to identify the acceptable level of safety. One source is standardization. Standardization bodies where people work together to define basically how we should do things in safety engineering, how we should make things safe. And the idea in the law is that when people meet there and define a standard and also defining the level of safety, that this is one hint to answer the question, what is acceptably safe? But it is also described in other sources. For example, there are a lot of commission recommendations, so especially now for European Union, a lot of recommendations and guidelines on product safety assessments. So this is also then from a legal body, at least a guideline and the level defined what needs to be considered for safe systems, and also answers the question on the acceptable level of safety. But there, at least in every engineering domain, we have a code of good practice, and this needs to be followed. This is strongly related to the state of the art of technology, state of the art and technology. That means when certain safety measures are known, safety measures are quite common, then this is a gold standard somehow. So you cannot establish something that reduces the risk and later say, okay, no, we don't want that because it's too expensive. When this is really state of the art, then this is the new level of safety, the new expected level of safety, because this is the next point. The directive also says we need to consider the reasonably consumer expectations concerning safety. This ultimately means that what was safe 10 years ago maybe not be seemed safe today. At least what was safe 50 years ago is not safe today. We see that, for example, in elevators or the old elevators, when they are retrofitted, they get additional doors. So you have a door outside and a door inside. When you go into the tramway, into a railway, there is also a sensor in the door, so you cannot be locked. This is setting new levels of safety, and we then need to follow them to achieve the expected slash acceptable level of safety. A little bit more about standardization. So the international safety standards reflect the state of the art and technology, as I said. But in the end, it is not mandatory to follow the instruction that are described in the standard. But you should have at least a very good reason why you're not following the measures and procedures defined in the standards, because it is reflecting the state of the art and technology. At least you should have the good reason when a judge asks you when something bad happens. So there is also a convenient thing, and these are harmonized standards. That means that some standards that are made by um, by bodies of the European Union, for example, you have the European Agency for Railway, and they are defining in a standardization process standards, and they are harmonized to law. That means we can presume that if a system was built according to the standard, and the standard is applicable, of course, then it is also conform to law. This is the so-called presumption of conformity. So we presume that the developed system is conform the to law and to the requirements set by law. So is it acceptable, safe? Why it is a presumption? So we still need to have an assessment. We still need to do all the necessary checks and validations and maybe also certifications. I don't know. So it is not enough to use the standards. And also we have to check if anything else what is not covered by the standard is source of for a hazard. So that means that we need at least to check, is our system really just the thing that is defined in the standard? You have maybe a machine, the machine is described in the standard, but you also have then the machine is built on a car. So then you need to follow the machine standard and also the car standard. And this is not a made up example, this is a fire truck. Fire truck makers need to consider it, most of the time two standards for all the machines on the truck and also for the car. Yeah, and one thing also to mention on technical safety standards or also functional safety standards. When we talk about them, we usually talk about standards for electric, and programmable electronic systems, which is for today's system not a big limit. So it covers probably every system that is that is developed today, but most of the standards does not cover any hydraulic or pneumatic systems, at least not fully. They can be part of the hazard and risk analysis. We can define the safety goals according to the standard, but the design and the engineering processes to get the pneumatic system cannot be done according to a standard that does not cover these kind of technology. Yeah, and functional safety is mostly dealing with safety functions. So it is functional safety is about the correct functions of the. It is on the next slide. The correct definition would be it is part of the overall safety relating to hazards caused by malfunctioning behavior of electronic and electric systems. It is called in the automotive standard. But yeah, in other words, it is dealing with the correct function of these or of system functions when the malfunctioning of this function could cause harm to people, properties, environment, and so on. Yeah, but what is the history of functional safety? Why it is defined like it is? In 1976, there was the Seveso disaster. It is now called the Seveso disaster in Italy, where a boiler exploded and toxic dioxin gas was set free. The explosion was due to a heat accumulation in a boiler that led to a chemical reaction and later also to pressure accumulation. What would have avoided the explosion would be a permanent circulation, so a mixer that would turn over the heat in the system, but there was no automatic cooling system. And this was the birth of the functional safety concept. So when there would be a sensor measuring the temperature on the correct places and would, in case of too high temperature, start a turnover process, a mixer basically, then the disaster would have been avoided. And that was basically the beginning of the functional safety concept. This somehow then developed further and further. The European Union developed the Seveso directives 1, 2, and I think also 3. They are mostly applicable to big chemical systems, big chemical machineries. But the functional safety concept was born and was also applied to smaller scale systems. But at least all these systems have in common that they can be the source of harm. So, okay, what are now the methods, metrics, and procedures in order to achieve functional safety? So, at the beginning, as I said, the concept was evolving, and during the mid 90s, the IEC 61508 was created. It is kind of a mother standard, but without a specific domain, and really just focusing on how to achieve an acceptable level of safety for hardware and software systems. The part with how to identify the hazards is not fully described there, what in other standards already is, but the classification is described. So the IEC 61508 also established the SIL concept, the safety integrity level concept. We then have in the standards metrics and processes that tell us, okay, when one part of the function under consideration, when there is one malfunction, for example, one resistor in the hardware circuit is faulty, do we need to be tolerant against that fault? For a low SIL, this is true. For a high SIL, it is not true. One fault it is not acceptable that one fault leads to the loss of the safety function. Yeah, and there are also processes defined. In every domain, we have a little bit different metrics, we have a little bit different processes, but in the end, they're never contradictory. You can also get to the point where you say, okay, when we consider this, this, and that, then they have the same meaning. But yeah, as I said before at the beginning, this is an attempt to highlight the common concept of all these functional safety standards. And one of these key ideas is that safe faults are good faults. If the failure of one component does not lead to a dangerous situation, let's say the loss of the safety function, the failure is not considered any further. So, okay, it fails, we are not in reliability engineering. The next point is redundancy. To detect malfunctioning behavior, additional redundant information is needed. So when we say, okay, one sensor failed, we need to compare that sensor somehow. So how shall we know that the value we get from the sensor is faulty? We need an additional sensor. So we need additional redundant information. This is again depending on the identified safety integrity level. For lower SIL, and also depending somehow on the domain and on the system under consideration, it is maybe not needed to have redundancy, but for higher SIL, this is a basic approach. If you want to achieve a high SIL, you just double it, trifold it, and so on. With redundancy, dangerous faults, when the failure of a certain component would lead to a dangerous situation, dangerous faults can be turned into safe faults via detection. So we have redundant information, we can detect them, and then initiate a safe reaction. We see that the sensors are faulty, we say, okay, stop the car should not move any further. And a common concept overall safety standards in all domains is that we have a certain metric that tells us how many safe and detected faults we must have in order to meet the requirements of a certain SIL. I have visualized that in this very sophisticated graph. So we have here a fault, and we can separate them in safe faults and dangerous faults. And dangerous faults can further be separated into detected faults. So then we have dangerous detected faults and dangerous undetected faults. And there is always a metric that somehow says that there must be a fraction of these faults that is at least safe or detected. And then we are calculating the share of dangerous detected and safe faults in comparison to all potential faults. This is a very popular concept for hardware systems where you can really apply that on a, let's say, where you look on what components do we have in our hardware circuit, how can they fail? So is it a shortcut? Is it an open circuit? And then we are considering, okay, what is the consequence on the system level when this happens? And then we can identify, is it a safe fault or is it a dangerous fault? The third principle is to reduce the probability of occurrence. I said before, we are not in reliability engineering, but reliable components are somehow needed to reduce the probability of failure. So as I mentioned, there is not always the need to be tolerant for one fault if the consequences are too low, but this is only effective for random faults only. I will come to that concept of random and systematic faults later. So, but for these kind of faults, typical example again, hardware components, resistors, any kind of condensators and so on, what we have on a hardware circuit must be also reliable, because even if we have redundant components, unreliable components could lead to problems, because when I have two unreliable components, the overall reliability of the redundant system is then lower than the reliability of one of these components when you calculate it with, when you, for example, have three redundant components and at least two must not fail, then the overall reliability would soon be worse than the reliability of one component if you have very unreliable components. I see that there is a question in the chat. I want to check if it's better to answer it now or later. Yes, the question was, what is the safety design approach when stopping a car or a train? For example, in a tunnel, that might be a huge risk. For example, if the train is on fire or the train control system is harmed by fire. This is this is a good question. So, for example, for trains, it is not allowed to stop in tunnels, and it is also not allowed in trains. And on each track, there might be additional places where you must not stop. This is considered, for example, when you pull a emergency brake, but you're in a tunnel, then the train will try to reach the next station. Don't try this, but when you pull the emergency brake in the Vienna Underground, the train will reach the next station before it stops. It just inhibits that the train proceeds the journey to the next station after that station. So a very specific question, but let me answer it a little bit further also. So you need to find at the end a concept that somehow works, also to avoid dangerous situations like that. So as I said, we try to reach the next station. There is also the concept of graceful degradation. So that means that we try to stop prior the. So we try to reach the next station, but if we can't reach the station, that the train breaks in the tunnel, but we have exit tunnels to leave the tunnel safely, and so on and so on. So there are additional measures to mitigate dangerous situations like that. So, okay, let's proceed. I see that we are a little bit behind. Additional procedures are also defined. So the whole functional safety engineering process is based on an established quality management system. So at least if something is not has not an ASIL, so is not safety relevant, it is considered that it is at least developed according to a quality management system, so in a quality management system environment, that we apply good engineering practice, and that we still have reviews, tests, verifications, and validations to check if all the measures and metrics are met. Two basic types of faults I mentioned. We have random faults caused by not directly predictable spontaneous processes in production and the use of components. Example again, we have an electronic component that was made, two electronic components that were made at the same time in the same production line. They will always be a little bit different. And these variation cause that the component will not fail at the same time if they apply it in the same way in the same system or in a similar system. This variation can be controlled via thorough process measures in the production, but they cannot be avoided at all. Aging and wear are also affecting the components, and sometimes they will fail. We cannot tell exactly when, but we can model it with a probabilistic model and can somehow predict, has it already failed, will it fail, and so on. Different to that, we have the systematic faults inherent to, these systematic faults are inherent to the system or the system setup respectively. They are somehow linked to human influence, and they cannot be described by a probabilistic method. So all the components which have a systematic fault nature, they will fail when the same conditions are met. They will fail at the same way when the same conditions are met. So all software faults, all software failures are systematic faults. So that can be classic programming bugs or just that we have a wrong software specification, but this is then a systematic fault. This leads us to the challenges of today's approach that is still in place in our safety standards. So the question is safety engineering reliability engineering, just to use more reliable components in order to avoid dangerous faults? So the spoiler is, as I said before, no, safety engineering is not reliability engineering. But why do we even consider this topic? As we saw, a lot of methods somehow are in safety engineering are quite old. We have the fault tree analysis, we have the failure mode and failure effect analysis. We are focusing on malfunctions of the system. So when something fails, that can lead to dangerous situations. This was, and also what I described regarding redundancy and how to treat dangerous faults and safe faults and dangerous detected faults. This comes from from a time when we mostly had electromechanical systems. We had a lot of electric, but not electronic hardware. Later, then we had electronics, but electronic circuit with resistors, capacitors, and so on. All this could be modeled with probabilistic models and somehow calculated. This was very convenient, and somehow the standards are still built up on that time. And yeah, when we had just all these simple systems with hardware components, we could just say, okay, make it more reliable, nothing will fail, everything will work without harming anyone. But the robustness against systematic faults cannot be shown with reliability metrics. So we need a new approach. We need to go away from the component failures, from the malfunctions, we need to find something new, because our systems are now not electromechanical anymore. We have a lot of software. Software is, as I said, has systematic fault nature. We need something new. So how shall we find what are the new methods sufficient for today's and future systems? And what shall we do to make new safe systems? So the problem is till now that if we have a hammer and we have all the tools, we try to apply that to the new systems. When all that we have is a hammer, then everything looks like a nail. And in our context, we have the FMEA, we have FDA, all these concepts, and try to apply them to software. This was okay until a point, but now we have a lot of software in our systems, and this approach will not be sufficient any longer. We have the challenges that we don't deal with random faults, where we simply can make everything reliable and have everything redundant. Our systems are very software intensive. And physical systems always had a natural constraint. And software provides us a wider solution space. So that also leads to the situation that we can implement something in software and don't see what are the consequences, that we are moving big masses and they could hurt someone. We don't see that if we probably don't see if we write the software code a little bit differently, that we can avoid maybe dangerous situations. So software is somehow decoupled from the reality, decoupled from the real consequences in terms of safety sometimes. And this is not the only problem, that we have a shift from random faults to systematic faults. We have also new type of fault, the component interaction failures. That means that components or subsystems all working as intended, may be also very reliable, but unforeseen interactions between them might lead to dangerous situations. I have two examples on the next two slides. I will skip them due to time reasons. But when we look at the Airbus example, we had a safety function that inhibited that the thrust reversers were applied before the plane landed. This was a safety measure, but the plane already landed, but the sensor said, no, we did not land because the conditions were not met. Everything worked as intended, but the interaction between these components was not perfect. So this has nothing to do with faults, with random or systematic faults. This is just an interaction fault. We have the first actions to tackle that kind of failures, system failures. For example, in automotive, we have the SOTIF standard, the safety of the intended functionality, where we're really considering just are the functional interactions in a way that we can avoid hazardous situations. So we need to focus on that. Another challenge for the future is artificial intelligence. Even though machine learning, deep learning, and so on can be seen as a way to produce software code, it is we cannot apply our standard methods to check the software if it's safe. So we have measures to make safe software in our safety standards, but they cannot be applied to that kind of software because it is different kind of software. So we need measures, we need standards dealing with AI-based software, because in most standards, AI-based software is explicitly out of scope. Are there any other intentions to tackle that problem uh, with safety in modern systems? Yes, we can apply approaches based on systems theory, model-based approaches, and first, and the most important thing is that we consider safety as a control problem. We need to enforce certain safety constraints. This must be our goal and not avoiding failures and faults. Our goal must be to say, okay, this is the state of the system that is safe, and we need to do everything that this state is kept. There is one accident causality model which is based on system theory and tackling and also this model-based approach and seeing safety as a control problem. It is STAMP, System Theoretic Accident Model and Processes, developed by Nancy Leveson at the MIT. And it is a kind of a control loop. It can also be hierarchically stacked. But the basic idea is that we have a controller that can be a human, that can be a computer, microcontroller, and so on. And there is inherently a process model. So when we think of humans, we have an imagination how a certain process works. We then have our sensors, our eyes, or we have a technical sensor when this is a technical system, and we feed that process model with these inputs. Based on these inputs and of this process model, we have an actuator where we are manipulating the control process. This is a very generic approach, but when we think it through, we can apply it to a whole bunch of modern systems and can then identify, okay, we have a hazardous situation. This can be caused by wrong sensor data, by inappropriate control actions, or by inappropriate actions or incorrect actions by the actuator, and so on and so on. There is also a yearly conference that is explaining and propagating this idea. But this is a new approach how to deal with modern kind of systems. Yeah, there is also the possibility to tackle that with model-based approaches like SysML. I will skip that also due to time reason, but we had a webcast last week where you can where you can have and where you can get an idea on what model-based systems engineering is about. Okay, we now talked about safety. We now talked about that we in future need to consider safety as a control problem, that we need to identify what is our safety goal, what is the condition, what is the system state when our system is safe, and that we need to do everything to achieve the appropriate level of safety and to keep the system in the safe state. And this is now the point where I see the relation to security. It was long. Somehow the definition I heard also in my professional career that security is about intruders, keeping intruders out. That safety is about no danger to the system environment coming from the system itself, and that security is to prevent any danger from the system coming from outside. That security is always connected to malicious intent, and that safety does not consider any malicious intent or misuse. Are they still okay or outdated? I would see they're outdated, because why are safety standards considering foreseeable misuse and somehow a malicious intent if we don't want to focus on that, if that is, we would say, security? So the hard limits, there are no hard limits anymore between safety and security, because safety standards started to consider at least foreseeable misuse. So when you say, okay, the design of the system is in a way that a controller might be led to unsafe behavior. So the boundaries were not that strict anymore. There are also a lot of other security considerations in the standards already. Most of them basically, yeah, please consider security also, but there is a whole annex in the automotive standard dealing with the interactions between functional safety and cybersecurity. And also the old standard, the IEC 508, is referring to big series of security standards for industrial automation and control systems. The IEC 62443 family, which is consisted, I think, of 13 standards. So they were already bridges between these two ideas on safe systems. We can see that we have also similar definitions of what safety is, what security is, what risk in security is. So we still have severity of the impact, but the probability is somehow described by a vulnerability and a threat. And what my impression is, when people see that vulnerability, okay, my system might be vulnerable, but threat, I'm not the target of an attack. Why would someone attack me? So a potential harm is often obvious. The vulnerability is also at least clear that there are some, but the threats are underestimated or at least misunderstood. Because they say, yeah, why should someone attack me? But it's not attacking you, it's about attacking you and 1,000 others. It's about that the threat is high when it is very easy to attack you. It's not a personal choice of an attacker, but it's more of a choice. Okay, you're an easy target. I will hack you. I will attack you. So, and people underestimated how easy it sometimes is to get into systems and manipulate it. So, this is for me, this is a reason why the safety was often, let's say, or not considered enough, and why this is a little bit changing, because they become aware, okay, they are not attacking me personally, but they are attacking me because I'm an easy target. Some definitions from standards, I will skip them also due to time reason, but I think they are clear to most of you. But you see here that these standards are already defining. So let's say this is a security standard, but out of a standardization body which was dealing with safety standards now. And maybe you can see, are they somehow in a way, are they defining cybersecurity threat scenarios and so on in a way you would define them as a security engineer also. So, but what is now the integrated approach between safety and security? So, based on the very long discussion before we discussed definitions, we can identify the common goal. We can identify, okay, we want to prevent harm from people, property, and the environment, and so on. And as I said, the new approach in safety should not be that we should avoid malfunctions, but that we should try to enforce certain safety constraints. And then when we treat the safety constraints, when we define the safety constraints, then we could treat attack scenarios as another causal scenario which could trigger a dangerous situation. So we say unintended acceleration is a hazard. Okay, how could an attacker trigger unintended acceleration? It would then not matter anymore if this is due to a component failure or this is due to a malicious attack. And also, not only on the goal level, we might find common approaches, but also in the methods which we want to apply to achieve an appropriate level of safety. Sometimes also the solution to prevent a certain event are the same. So when we have an chemical plant where an centrifuge must not spin faster than a certain speed, then we may have a mechanical construction that prevents the centrifuge from spinning faster. When it tries to spin faster, then there is a block, a brake that prevents it. This could help to prevent spinning a centrifuge spinning faster than a certain speed limit for due to a malicious intent, due to component interaction failures, due to component failures, malfunctions, and so on. A second example, when we think of a boiler and we have too much pressure, we might have a valve that can prevent overpressure. And then it would also not matter if the pressure accumulation was due to a malicious intent or due to a malfunction. So I don't want to say we don't need to consider firewalls and so on to keeping intruders out. But one of the steps is simply just to prevent that a bad situation can happen with a valve, with a mechanical construction and so on. And this helps both safety and security. Yeah, my outlook and summary. The difference between safety and security will not matter that much in future anymore, because today's systems are very complex. The complexity will increase further, and exhaustive analysis to check if a system is safe or not are not feasible anymore. We have too many different system states. Yeah, and this will lead to the mentioned focus shift. The focus shift is already taking place. It's not about failures and faults. It will be about enforcing safety constraints. And then the classic definition for safety and security will become more and more obsolete. And someday they will be obsolete. The question will then be, is the difference relevant or is it not relevant to make systems safer, respectively more secure? If you can answer that a question with yes, this is relevant, then maintain the difference, please. But I would predict that the answer would be no, and then we should not care for the differences just to have a difference. There will still be some differences in the approaches, in the measures to take, and so on. But we don't need to keep the boundaries between safety and security higher than they need to be. So the initial question was safety and security, same, contradictory, or just different? At the end, I would say all three options are wrong and true at the same time. For sure, we will find cases where it is contradictory. We will find cases where it is the same, but in most cases, it's just different. Yeah, thank you for the attention, and I apologize for being way too long, for talking way too long. But if you still want to hear more and still want to hear a little bit more about safety, I just want to highlight also my podcast, Safety Corner. It is available on all common platform streaming, podcast streaming platforms, and also on my website, on the podcast website, safetycorner.wagnerflorian.eu. Thank you.
Thank you very much, Florian, for being part of this meetup. There is one more question in the Q&A section. I will read it out loud so that everybody has it also on video. The question is, from my understanding, one of the conflicts between security and safety practices is that safety is about designing and thoroughly testing, so certifying a system and never changing it afterwards, while security needs constant updates. Is there an idea in safety standards how to address continuous updates without having to go through the long and burdensome process of having to recertify the whole product, for example, medical product, pacemaker, plane, etc.?
So the first answer is, unfortunately, cannot tell which standard this is already covering. But yes, there are a lot of approaches to have updates, because when we have more software intense systems, it is clear that we need to have the possibility of an update. Regarding the certification, so we cannot just update something without certify it. but it is not about recertifying everything. We just need to certify the possibility for updates. So we have a system that has the possibility to be updated. And when we define that, when we certify also the update possibility, then we can establish, and this is now part of the discussion, still ongoing discussion, but then we can say, okay, for an update, these and these tests must be carried out. Maybe just a quick review because it is just a small thing, or we really need thorough tests. But yeah, we will then for sure find a good solution how to update things without recertifying everything. But the key is again that we need to consider the possibility for updates in the first place.
So I have another question. So if there's any other question by the attendees, please post them to the Q&A section, or you can also request to speak live. So you can also ask the question live. So there are a few parallels between the safety and the security world is now one of my conclusions of this talk. And one that I found particularly interesting is that you also said we need to mitigate things or bad things to happen by design. So that relates to also designing security into products. And the activity that is behind to find those threats is threat modeling, right? And one way to do threat modeling is to say, look, these are the components, these are the interactions and data flows between them. You draw trust boundaries, and you have a categorized list of threats, threat types. One very common model is STRIDE categorization. So you have spoofing, tampering, repudiation, information disclosure, denial of service, elevation privilege. And then you can say, let's think about spoofing. How could someone say they are someone else in that system when the data crosses the trust boundary? Is there a similar approach or similar list of categories that are bad things that can happen in terms of safety, and a similar approach like threat modeling is in security?
So I'm sure when we sit a long time together, we can find a way, the full bridge. But the short answer would be no. I cannot think of a really similar thing to that. The only common approach is somehow. So what we have, what maybe needs to be stressed, this is already you're talking about security by design approach. This is something what I mentioned is somehow missing or not fully developed in safety. There are some methods, they have keywords where you say, okay, too high, too low, and so on, but this is not really the same. And maybe there is one, and maybe this is the answer is in the chat, but at the moment, I cannot think of anything really similar to STRIDE.
Philip says, what about FTA and FMEA? They have pretty much similarity with threat modeling.
Yeah, so the concepts from a very high level perspective, they are same and you can apply them to them. It is a little bit about so when we look really how FMEA is defined, it is for me a classic FMEA in how the safety standards see them. FMEDA, for example, they are about, okay, how is a component failing? You have then the failure modes. You see, okay, this, as I explained before, you have an open circuit, a short circuit, or maybe just an value drift, and so on. And then you see what are the consequences. You can really describe that well. You used it in combination with the probability model. That being said, there are approaches to define a software FMEA. There are also certification bodies that propagate these methods that you can apply FMEA to software. I am a little bit, I don't see that this is really the best approach to use a method that was defined for different concept and to put it on software, for example. Yeah, you can maybe look on it. So for example, FDA, when you have a clear software architecture, you can say, okay, if this fails and this software component fails, then this can happen. Look what are the good things in FDA, FMEA, take them, apply them. Yeah, okay. But really to say, okay, we are now applying FMEA on software when the initial idea was totally different, at least I would be careful doing that. And regarding the similarities, yeah, you can for sure you can find things that are similar in threat modeling and FDA, FMEA. That's true. But I was more focusing on Stride. So this, yeah, okay, maybe Philip is right. These are the failure modes, for example, and then we can find similarities between FMEA and threat modeling. But at least we are not on the direct level to say, okay, FMEA can be applied to software, FMEA can be applied to security, but we are taking the high level ideas. And this is a good thing, to take the high level ideas and to apply it into a new context when this is helpful.
Cool. Thank you very much. As far as I can see, there are no more questions. Again, please also share the link to this talk. We will put it on YouTube, and we will share the link to the YouTube video in the meetup group. So feel free to share it with people who might be interested in this. Florian, thank you very much for being part of this meetup. And now you're part of the meetup family, and you will be asked to hold more talks about safety. I can assure you that.
Okay.
Very interesting talk and very interesting topic, side topic to our basically security meetup to broaden the view. Thank you very much, and thanks to all the attendees for being part of this today. And see you at the next meetup. Have a nice meeting, everybody.
Thank you also for the invitation, everybody. Thank you also for the invitation.
Right. Have a good one, everybody.